Hey guys, this is to help you with understanding endothermic and exothermic reactions as well as activation energy. So this should help you on number 1 and number 2 in terms of the diagram that they're referring to. So if you look up here, we've got heat on the side and time over here. So one of the graphs is going to start low and end high, and the other one is going to start high, still go up, and end low, something like that. Obviously, I'm not a perfect artist. The key here is what you see though. This starts low and ends high, whereas this one starts high and ends low in terms of heat. So it has low heat and then high heat. So that means that this system is gaining energy. This is gaining heat or gaining energy. And so if it's gaining, then that's going to be an endothermic reaction. It's getting warmer inside. So that's going to be an endothermic reaction. Over here, you have high energy and then it dips down at the end. So you've lost energy. So there is a lost energy there. You're losing energy. That means that's going to be exo. So for you, for day my worksheet, that should help you figuring out which graph goes with which question. So then giving you an example of the table. This is the one I did in class. So an ice cube melting on the table. You first have to decide which of these two things is the system, and you can choose either thing, either an ice cube or the table. So I'll show you both examples. So let's say I choose the ice cube. I need to think about what's happening to the ice cube. So it says that the ice cube is melting. Typically, in order to melt ice, you add heat. You might put it out in the sun or put it on a stove or whatever. You're going to add heat in order to melt that ice. If you need to add heat, then it is taking in energy. If you are adding heat in order to melt it, it takes in energy. So it's endothermic, and then I would explain to some degree like the ice cube is taking heat, which is taking in heat, which is how it is melting or something like that. Now, I could have also chosen the table. So there's no like one right answer for this system. It's really a matter of if you're lining up this system with the correct answer over here. So if I chose table, I have to think about its relationship to the ice. So the ice cube is sitting on the table. So that essentially means that the table is melting the ice. If the table is melting the ice, it means it's giving away its heat, which is why the ice cube is melting. So the table is releasing heat to the ice cube. That makes it's an exothermic reaction. And then to explain it, I would basically say something like that. So the table is transferring its heat to the ice cube, making it an exothermic reaction because it's losing its heat. So that's the data table. For the back equation, there's two different parts. So this is going to be kind of for parts question 1 through 4, and then over here for 5 through 6. So focusing first on question 1 through 4. Come on, Kitty, get that. Oh, I know, life is hard. Okay. All right, so inside the equation, if you're looking at it inside the equation, meaning the chemical equation, so generic example, A plus B arrow C, A plus B arrow C, we've seen those before. The addition that you're going to see is kilojoules, some kind of kilojoules. And what we're going to be looking for is where are those kilojoules? So on this one, I can see that it's on the left side of the arrow. That would also mean that this is where the reactants are. So that means that the kilojoules, the energy, is a reactant. Okay, so the left side and a reactant. Over here, it's on the right side. That also means that it's a product. It's something that's being produced. Okay, so everything over here are the products, everything over here are reactants. If it's on the left side, if it's a reactant, that means we're adding energy in. Okay, this is kind of the inside and this is the outside, releasing it to the environment. So if the kilojoules are on this side, it's going to be endothermic. We're adding it to the system. If the kilojoules are on this side, we're releasing it. Think of it as like dynamite plus match equals explosion. That's going to be a release of energy. It's going to be producing that energy. So then it's going to be exothermic. So for questions 1 through 4, you're looking at what side it's on. So if it's part of the chemical equation, is it on the left side or the right side? Now notice that there's no negatives here. It's all pluses. It's not even, I wouldn't say positives. It's pluses because you're adding chemical A plus chemical B plus energy. You're never going to see chemical A minus chemical B. You're never going to see minuses in a chemical reaction. So that would be true for the energy as well. However, if you have it outside of the equation, it is possible to have negative symbols. So this stands for delta H. For our purposes, let's go ahead and call it change. Delta means change in heat. It's actually enthalpy, but let's not get into that. So change in heat. If you have, there's really only two choices, negative kilojoules or positive kilojoules. So remember, this is outside of the equation. This might be listed prior to the equation or after the equation exists. On the worksheet, it's after the equation, if it's negative kilojoules or positive kilojoules. Now for this one, think logically. If it's negative kilojoules, does that sound like it's losing heat or gaining heat? To me, a negative implies losing heat. And that's going to be the same as what's up here. Losing heat is exothermic. So if you see a negative kilojoules on the outside of an equation, that's going to be endothermic. And then, of course, the delta H positive should be the opposite. If you have positive kilojoules, then that means it's gaining energy, it's gaining heat. And then that's going to be an endothermic reaction. It's being added to the system. Okay, so that would be for questions 5 through 8. These ones are a little easier to see logically. Sometimes people have a little more trouble with this one, so you have to kind of think about it a little bit. And then for the last section, if you did not pay attention in class, I have a generic example, not the one we did in class. That's a perk of paying attention in class. But I do have an example to walk you through how to do those graphs. Okay, so you'll see a graph, something like this. These are the numbers that I input. Wherever the graph starts is always the reactants. So in this case, my reactants are here. My reactants are wherever I start. My products are wherever I end. So my products are going to be over here. Hopefully I'm not smudging this too bad. Okay, a couple other words on here that we want to know. The very, very top is called the activated complex. And I'll talk to you a little more about what that means when I finish labeling. From wherever we start to the top. Okay, from wherever we start, it doesn't matter if it's high or low, it doesn't matter. Wherever we start to the highest position, that's going to actually be called our activation energy. So our activation energy is really important. What it tells us is the minimum amount of energy that any reaction needs in order for the reaction to occur. Every reaction has some amount of activation energy. So if you look up at our original diagrams up here, this one actually doesn't have so right here, that would be the activation energy from where we started to the top. This one doesn't really have as much energy. Again, it's always from where we started to the top. So you don't need all that much energy for this reaction to happen, but you need a lot of energy for this reaction to happen. Every reaction needs energy, and here is why. So think about it this way. Let's say I have A plus B, or AB plus CD, and we're going to switch it to AD plus BC. Just generic equation there, okay? Let's pretend this is a polar covalent bond, just so you can see the bond. Okay, so A dash B. And then over here, let's say this one is too, so we'll do B dash C. If you notice, the B is attached to the A here, but the B is actually attached to the C here. So in order to make this bond happen, I actually have to break this bond. There is some type of bond that has to be broken. And I think of breaking bonds like I do breaking bones. It's actually even almost spelled the same way. Break bonds, break bones. Okay, the reason is because I know that you need a lot of energy to break a bone. Usually there's some kind of significant force. A football player hits another football player. A line drive ball hits you in the skull. You're trying to do a triple sow cow in your front yard in the mud. And there's a large amount of force that could be gravity or whatever it is. And that's typically how you break a bone. So I know that breaking bones needs force or energy. So does breaking bonds. You need energy to do that. What's cool is when you're making bonds, so when we reform this bond, you actually make energy. So you use up energy here to break the bonds, and you can remake it when you make new bonds. So that's why everything will have some kind of activation energy. There's always going to be kind of a top of the hill. There's always going to be an activated complex because of that. Okay, so and I'm going to help you guys to figure out how to calculate all of these. The last thing on there is delta H, or the heat of reaction. Okay, and I'm going to break down how to figure these out. Okay, so first of all, the easy part, so reactants. The questions talk about the heat content of the reactants. All they're saying is, how much energy does the reactants have? Well, guess what? I'm just going to call reactants here, react. It has 20 kilojoules. Let's see if I labeled this properly. Kilojoules of energy. The reactants have exactly what it says, 20 kilojoules of energy. Cool, let's do something else like the products. That should be easy too. It's really just making sure I can read the graph. Where does it say products? Right here, 50. The products have 50 kilojoules of energy. How about the activated complex? Let's figure that out. That is just a value as well. The activated complex is the top of the hill, 150. So my first three answers is just literally looking at the period or looking at the graph. Next, we have to do some small calculations. Okay, so the first one we talked about was the activation energy, and that's always going to be the top, so the activated complex. I'm going to just call it top for now because it's a lot smaller to say. Woo. Top minus, let's see where it goes, the reactants, or where you start. So I'll say top minus reactants. So in order to figure out my activation energy, I just need to do top minus reactants. That's pretty simple math. So the very top is 150. Very top is 150 minus my reactants, which is 20, way over there. There's the 20. So I would just do 150 minus 20. That's going to give me 130 kilojoules to figure out my activation energy. Okay, lastly, my delta H. Okay, delta H meaning change in heat, change in enthalpy technically, but change in heat. According to the arrows, and these are on the graphs that you have, it's in between products and reactants. So in this case, it's actually always products minus reactants. Always, always in that order. No matter if it gives you a negative or positive answer, don't worry about that. Always do it in that order. So in this case, products is 50 minus my reactants, which is 20. 50 minus 20 gives me 30 kilojoules for our delta H. That's how you do these graphs. So you have two practices on that back sheet if you weren't in class or didn't pay attention, but this is the process to do it. Keep in mind a little reminder, a little math flashback. If you have, let's say, 50 minus a negative 30, if you have 50 minus a negative 30, that's not 50 minus 30 equals 20. Sorry. This actually becomes positive, and negative plus a negative equals a positive, so that would be 50 plus 30, and that would be 80. All right, my camera just fell, so we're going to call that a day. Have a good one.